So good afternoon. So today I'm going to talk about the internship project that I did in summer 2012 with ExxonMobil Upstream Research Company. And as you see in the title, this is a geophysical tool, the electrical resistivity methods that we want to use it to map subsurface features, topography at the Devonian. And as part of the assignment that I had, I was supposed to perform some assessment on previous measurements that they have done at Exxon. Just to mention, for the internship objective, when I went to Exxon, I was told that typically ExxonMobil contract another service company to collect the electrical resistivity data for them, as well as perform all the analysis, and then they eventually deliver the results to Exxon. However, in that recent survey that was done by the contractor, they performed the same survey on two different fields, which were close to each other, and one of them was successful in mapping the Devonian, and one of them was not, and they were not sure why and what went wrong. So we wanted to have an assessment on their analysis, and at the same time we wanted to design a 3D survey, because the previous survey that was done by the service company was a 2D survey. And they wanted to do a 3D survey, so as part of my assignment I was eventually designed a 3D survey for ExxonMobil, which was manageable and logistically manageable. And I also performed some 3D electrical resistivity sensitivity analysis, and eventually I was able to perform some immersion tomography to see the subsurface. With that, the outline of the talk will be, you will see a background and about the project, and also the geology in the region. And then I'll just touch briefly what is ERT, or electrical resistivity tomography method, and then I'll jump into the 1D and 3D analysis that I have, and then summarize. So this view graph shows, as the title shows, this is called the Athabasca Oil Sands. The project is located in northeastern Alberta, Canada. As we see it in this layout map, this is the Alberta, and the fields or mines are located in this region, and this is the Athabasca River passing through this region. And the top photograph was taken in 1900, and this is the Athabasca River, and you can see this highlight yellow lines, just for your eye guide, to show that the tar sand could easily be seen on the bank of the river, and that's why they call it the Athabasca Oil Sands. And it was in 1719 the European fur traders, they noticed that the people at the region used the tar to insulate their boats, and it covers over 141,000 square kilometers. It has 1.7, it's estimated of course, 1.7 trillion of equivalent barrel of oil. So you can imagine that this is the largest crude oil bitumen in the world. And that's now let's take a look at the geology, what makes it so rich in hydrocarbon. And of course I'm not a geologist or stratigrapher, but this is a stratigraphy section, as you can see here. The region, in a short glance, you can tell that the region has been divided into three formations: Devonian, and then we have McMurray, and then Wabasca on the top. The McMurray formation has been divided into two different sections by the companies or the geologists. One is called the Lower McMurray, and the other one is the Upper McMurray. And so the lower face or the bottom part of the lower McMurray is a bridal river with the fluvial deposits and with the early transgression or spread of the coal deposit at the top. And then on the bottom face of the upper McMurray, as the sea level, with the rapid sea level rise, there were some deep estuaries, as well as, mainly it's meandering rivers. So you can imagine that how the sedimentation, point bar sedimentation has been deposited there. And with some extensive flooding in the region, there were some that led to the formation of the deltaic and large bodies of brackish waters in that region. So that's how, we can see that how the organic materials have been deposited in this region. Just to emphasize that the bottom phase of the upper McMurray has been identified to be the main host of the bitumen and the formation. However, you can find, as I have highlighted here, the bitumen anywhere within the McMurray formation. But this region is the main host, so that's why you will see further in my slides that my model is also based on that part. And following that, again, the sea level rose, and so there was we had tidal flats, as well as the channels and point bar sedimentations were replaced by overbanks and vertical, deeper brackish bays. And then on top of it we have the La Vista. Just to summarize, about the geology, this region belongs to the lower Cretaceous, which means that it is something around 100 to 140 million years ago. And also the deposit is coming from the fluvial estuaries and marginal marine deposits. And so as it's basically highlighted here, we have the Devonian here, and why are we interested in mapping the Devonian there? That was the part of the project, when you looked at the title. So twofold, the answer is twofold. First of all, there is no permit by the contract to drill at or beyond the Devonian. There's penalty, and because there is no permit to the minerals, we don't have it. And at the same time, it has happened by other companies like Shell. When they dig into the Devonian, they flooded their mine with water. There is water aquifers inside the Devonian, and so therefore there's hazards to flood the mine. So that's why we have to know where the Devonian is. So how are we going to map the Devonian? Of course, we can use different geophysical tools such as seismic or electrical methods, electromagnetic methods. So unfortunately, because of the proprietary data, I cannot disclose the seismic with you. But in this project, I'm going to show you the analysis from computational point of view on the ERT method that we use to map the Devonian. So as you must have guessed, so to map the Devonian, we are going to use the electrical resistivity methods. So what is the electrical resistivity methods? So I think these are quite the standards. And in the electrical resistivity methods, what people do in the field, they take a car battery, and they have some electrodes, 4 electrodes, current electrodes and potential electrodes. So they inject or energize the earth with some electric current, and then once the current passes, let's say from this point to this point, then there will be some voltage drop in between, so we basically can measure the voltage drop using a voltmeter. So, and using the Ohm's law, we can easily identify, the resistivity. Of course, as you see here, the resistivity is proportional to some factor, which is called the geometric factor. This is related to how you put these electrodes with respect to each other. For example, here it's called the Wiener-Schlumberger configuration. This is a dipole-dipole, configuration. And just to mention that later on I will talk about offsets. So by offset, for example, here I mean that it's the distance between the midpoints of the current electrodes and the potential electrodes. So I can be at close offsets or I can go at far offsets. So no matter which configuration that we are going to adopt for our survey, we have to always consider the 4 important characteristics in that survey. One is the depth of investigation, how deep we want to map the structure, and the sensitivity to vertical as well as horizontal features that we have at the subsurface, and what is the data coverage on the horizon, on the surface, and also the signal strengths that we have. So here I have a comparison of these 2 commonly used Wiener-Schlumberger and dipole-dipole arrays for ourselves to compare. Just to emphasize that the model that I have is based on dipole-dipole because it is fast and it can be done faster on the field. So as we see here, dipole-dipole has a good vertical resolution. So in order to map some vertical structures like dikes and cavities, it's better to use dipole-dipole. If I want to map horizontal resolution, then it's better to go with another array like Wiener-Schlumberger. And it has low signal strength. As we go farther away, we go to farther offsets. So also we have to consider that into account. And however, Wiener-Schlumberger has got reasonable, vertical and horizontal resolution, but it's better for horizontal resolution, good signal strength, and depth of investigation is not that bad. So how do I basically perform the computational simulation, or how do we apply ERT in our simulation? So in this diagram, I just typically we have to simplify our model. So typically in geophysicists, they assume that the Earth is like a layered cake. So you have some layers by knowing some the conductivity as well as because conductivity and resistivity are related to each other, reciprocal. So if by knowing the conductivity in any layer, then solving some equation, I promise this is the only equation that I have in my presentation. So this is the Poisson equation where V is called the voltage drop and I is the current and sigma is the conductivity. Then we can, once you inject the current passes through each layer, and then once you're coming back, numerically speaking, you can measure the voltage drops and coming back all the way to the surface. And then you can, once you have the voltage drop, you can go back to that Ohm's law and connect it to your resistivity. So this is just a view graph, to show you, how we are going to model it. Let me just go over to the analysis and the results, which is more clear. So first, as I mentioned, in my analysis there will be 2 sections. First one will be a one-dimensional forward modeling analysis, and the second one will be the 3D electrical resistivity survey that I designed and performed the sensitivity. And this analysis that I performed was on the assessment on the job done by the contractor. We wanted to see what went wrong that they couldn't map the Devonian. So in order to perform the analysis, a good starting point is to know the geology, because I wanted to mimic the Earth. Now, in order to simulate the Earth, I need to know how the geology is changing in the region. So the very best position that I should go and basically use it as a reference is looking at the resistivity logs, because I'm dealing with the electrical resistivity method. So it's better to go see how resistivity is changing with the depth. So if this is depth and this is the resistivity, these are some measurements done at the borehole. So, and by looking at the resistivity and coming back to that geology in the region, so I just picked some of the layers just to show you how my layered earth model is going to be in my modeling. So for the near surface up to 20 meters below the surface, I said, okay, I can consider this is the Wabisca formation. And then I have the less resistive upper phase of Upper McMurray, and then I have the very high resistive lower phase of the Upper McMurray. Just to remind you that we said that the lower phase of the Upper McMurray is the main host of the bitumen, so it is hydrocarbon, so I expect to have a higher resistivity in this region. And then below that, this is, below that, this is where I have the Lower McMurray. And this is the drilled well, so the driller, we assume that, this is the top of the Devonian. They're not going below that. So I can put the Devonian anywhere, because when I looked at there were different, I don't know, maybe, I don't remember exactly the number, but there were, I think, more than 1,000 wells with the resistivity logs. So when I looked at several of them, I just picked some of them randomly. And in most of them, you could see the Devonian, or the maximum depth that the driller has gone. It was 50 meters or 150 meters or 100 meters. So the Devonian basically, is changing in the subsurface, the depths of the Devonian. So I can put the Devonian anywhere, somewhere between 80 and 150 meters, in my models. So, and having this information, I can make my layered earth model to feed it into my code. And as you see here, this is step function, is basically, that models. And I have, to perform the analysis, I perform two different models. One is when I assume that hypothetically there is no Devonian. So in other words, by the time I reach to the top of the Lower McMurray, then below which, whatever it is, I assume that it is completely Lower McMurray with the same resistivity. So that's why, if you see half the space, by half the space means that, wherever you see below that, has got the same resistivity. Another model is, if you can see the color, if you can tell apart the color, this is the red color, and this is where I assume that the Devonian is. Okay, so, and the arrow shows that this arrow can move up and down. Basically, it tells me that where the Devonian is. Devonian can go up and down in my model. So if I use this model, and now the question is why the contractor could not see the Devonian, okay, using the ERT. Now let's take a look at the analysis that we performed there. So what you see here is the resistivity versus the offset. So the offset, remember, that was the separation between the two electric current dipoles and potential dipoles. At small offsets, up to 400 meters of offsets, there is no separation between the two models. The red shows where I have the half the space at the Devonian, and then the blue shows where I have the half the space at the McMurray, Lower McMurray. So there is no separation between the two. So, and by the way, this is the maximum offset that they use in this survey line. So they didn't go beyond that point. So that's why, perhaps that's why, they couldn't go, they couldn't see the Devonian. However, since, the advantage of computer, we can go, farther that. So I went beyond that point, all the way up to 2,000 meters, and I could see that, as I go beyond 400 meters, these two separate models starts to diverge from each other. So, this tells me that, okay, if the, if I recall it correctly, this was for this simulation, I had the Devonian set at, maybe 100 meters. But now the question is how sensitive the ERT would be to map the Devonian, because we noticed that the Devonian can change, from area to area. It can go from 50 meters below the surface all the way up to 150 meters. So in this wave graph, perhaps this is more eye-appealing. This is the depth of the Devonian. Assume that the Devonian is 80 meters, 85, 90, all the way up to 120 meters, hypothetically. And what you see here, I plotted the ratio of the resistivity where I have the Devonian and to the model that when there is no Devonian, hypothetically. Okay? So, and the blue region shows where the ratio is 1. That means that there is no sensitivity. So no matter where the Devonian is, either 80 meters all the way up to 120 meters, we can see that, all this region is blue. That means that there is no sensitivity at all. However, if you want to have sensitivity, then you have to go farther and farther beyond. For example, if the Devonian at some region is at 120 meters, then we have to go all the way up to 600 meters of offset to be able to capture it. So therefore, as the title of this slide shows, the contractor needed to go to larger offsets in order to detect the Devonian. But that, let me also mention that, we also performed some other analysis in order to map rich bitumen area using the ERT. And in this presentation, I'm not showing the results, but if you're interested, I can discuss it later after the talk, because it was going beyond that, my time with it. So now let's move to the 3D ERT survey. And this is a schematic cartoon that you see. These are some current dipoles. A shows the minimum separation between the two dipoles. I assume that these are 5 meters, dipoles. And the green ones are the potential dipoles. Okay? So, and for this basically cartoon shows you from the surface. So you can see the surface, and if each of these black lines are one of the survey line, and the red symbol shows where you energize the earth with the electric current, and the stars shows where you read the potential. Okay? As you see here, either you are reading along the same line as you have energized the earth, or you can read in any other directions or any offline directions. So therefore you can have a sense of 3D feeling in this survey. And also another thing is, to get the concept from the seismic data acquisition, so we can use the roll along method. In other words, instead of removing all the electrodes, we can just move one of them, one of the survey lines, and roll it along, and therefore by this we can easily and logistically easy to manage, and therefore we can cover a larger area in a shorter time. And so we use the, okay, so now that we know what is that survey, these are the optimized survey parameters that I have in my model. And this is north going up, and south north is 240 meters, my model size in the computer, and from east west I have 1200 meters. Okay, and each of these lines is a survey line, and the minimum distance between each two consecutive basically lines is 5 meters or 10 meters. And these are, of course, some information regarding what dipoles I have taken, but there was some measurements of around 7,000 measurements of voltage difference, and with a 253 independent source. And the maximum offset that I went was 700 meters, and the minimum offset that I had was 17.5 meters. And so now that, I mean, this model, I mean, we have these optimized parameters. We wanted to see how sensitive the ERT method could be to the topographic features at the Devonian. For that, I have 4 different models. So let me show you this photograph. This is a photograph from the region. I mean, as you see here, I mean, this is the river passing, and at some point of this region, the Devonian is like an outcrop that's on the surface. And so this is the McMurray Formation. And so in my model, I have 4 models. One is if I have a completely flat Devonian, and the other one is if I have a dome shape or like a hemisphere at the Devonian, and or if I have like a bump sweep, like a semi-cylinder, I mean, shape at the Devonian with dipping in either northeast, north-south, or east-west. And so here I'm just going to show you the results on the dome-shaped Devonian. And let's take a look at the results. So what you see here is the sensitivity versus the offset. The sensitivity is defined as the resistivity when I have a dome shape in my Devonian, with respect to when the Devonian is completely flat. So it's just a percentage difference between the two. Okay, that's how I define the sensitivity in my calculation. And this cartoon shows how my model is. So as you see here, I have some flat layers, and the bottom layers is where I have the Devonian, and this feature is some hemisphere with a radius of 40 meters. So the reason being that we chose this hemisphere, when we talked with the drillers, they had the concern that there are some topographic features, I mean, like a hemisphere or something, and it happened that several times that they were, about to drill into them, and that could, lead to, as I mentioned earlier, flooding the mine. So we wanted to see how sensitive this method could be to basically capture that feature. So I performed 2 different simulations. So let's take a look at the sensitivity versus the offset. So as you see here, there are 2 different data points here. One is blue and the other one is red. The blue one is, I assume in my model, what if the McMurray has a resistivity of 600 ohm meters? Okay. Now I wanted to see how that survey that I have designed could manage to capture the Devonian. So now, if you look at the sensitivity, you can see that around 120 meters something, 120 or 110 meters of offset, up to this point, there's no sensitive, it's not sensitive at all, and if we go to 120, it is starting to pick up something around 2, 3, 4% of sensitive. But if you go to 500 meters of offsets, if I separate the dipoles up to 500 meters, what I'm seeing here is this method is almost 20% sensitive to capture that feature. And another interesting thing is, it is capturing the feature of that topographic shape. It looks like, to me, it looks like a semi-circle, which is part of that, cross-section, like this. And, but once we go to farther and farther offsets, we see that the sensitivity is dropping. The reason is twofold. So one is, we are losing the signal strength, and the other one is, as we go farther and farther away, these 2 models, the flat and dome, will become, similar and similar. So therefore, this difference will be less and less. So therefore, the sensitivity is dropping. And and another modeling that I did is, what if the McMurray Formation is rich and very rich in the bitumen, so therefore, the resistivity, its resistivity, let's say, it's 1500. So how sensitive my method could be to capture the Devonian, and by that, if you look at the red symbols here, you can see that, okay, generally speaking, the trend is similar to where I have the lower resistive McMurray. However, I could see that at any offsets, this sensitivity has been suppressed. Especially at 500, if I look at the 500, I could see that it's been almost halved, or 10% drop in the sensitivity. But that now that we performed some sensitivity analysis, another interesting or cool thing could be how to map or how to image the subsurface. And that was basically, performing some inversion methods in order to capture these, cool pictures of the subsurface based on the resistivity. And for that, I performed some inversion. And just to mention, these results I collected them right in the last day of my stay at ExxonMobil. So, and there are still preliminary results. These are not final images. And this was done on like a bump-shaped feature that we had there. 3 different cross-sections I have provided here. This is the west-east, and this is the depth. And this is from the surface, so I'm just going into the depth of 65 meters below the surface. And I'm looking at it from the south, north, and west, east. So it's a cross-section. And this is depth, and this is south, north. And so the good thing about this inversion, even though they are not finalized, is they started to pick up the structure. So just to mention that this structure was like a semi-cylinder protruding from the Devonian into the lower McMurray as well as the upper McMurray. So as you see here, the blue region is the lower McMurray and the green region is the upper McMurray, and then the red one is the Devonian. And as you see here, the code has started to pick up this the shape of this feature, which is if we want to be very idealistic, this looks like a semi circle. And if you look at this cross section, so if you look at that, you can see that the strike look like a rectangle. So you can see that all this region is. By the way, the red shows that where you have the high resistive materials. So the color coding goes like that. So where you have the high resistive materials. And also, when we look at this cross section at the depth of 65 meters, we could see that the code is picking up the high resistive materials. So just to summarize, we performed some analysis, assessment on the ERT performed by the contractor, and we noticed that they have not used large enough offsets in order to capture the Devonian. And I designed the 3D ERT, which I showed that it was logistically manageable and easy for the company to perform. And also this 3D ERT, based on the analysis that I performed, they were sensitive to the Devonian topography. And the results that I did not show to you today is sensitivity analysis indicate potential for mapping good ore using ERT methods. So, and further suggestions, I initiated the inversion, so continue inversion on 3D ERT as well as using other configurations for the arrays to have second opinion, and as well as finding better resolution on other features. By that, let me acknowledge ExxonMobil Upstream Research Company for providing the financial support for this to perform this research and internship. And my mentor Jan Schmiedes, team lead Danny Villan, and my supervisor Grant is. And the rest of the members at the electromagnetic potential fields at ExxonMobil. Also at Rice University, I would like to thank Professor Dave Sawyer, Professor Dunlop, and Dagmar, and also Emily and Mary, Liz, and all the other faculties at the Earth Science Department, and also my wife and my son. Thanks so much.
Any questions?
Ollie, I really enjoyed reading your paper, and we got common interest in this. You used Loke as one of your references.
Yes.
He has a really good white paper on the whole methodology. If you talk about his median depth of investigation, which he likes to use as a way of measuring how deep you can look at what offset, if you look at the endpoints of the winter Schlumberger and the dipole, boy, you're barely getting there with 600. If you have 120 meters. So my recommendation is deeper yet. And in a practical sense, depending upon who they use as a contractor, you probably need not the 28 electrode array, but the 56 with 20 meters, and that'll get you down the road faster with your roll along. But you'll also be able to look down, even 150 meters and more, because you're barely, with 600 meters, you're barely seeing the 120. Looking at the endpoints of the
That's
sources, it's as you say in the text, at least an offset, and I agree with that.
Okay. Yeah.
So, the only other question I had is, why are you recommending the two, winter Schlumberger and dipole? Are you worried about losing signal strength from the dipole?
Yeah.
Go to the stronger winter?
That's true.
Okay.
Because it's just a battery, car battery, so.
Yeah, you probably need a booster box on that. And
Okay.
you probably got to kick down all the noise of the plant somehow.
Okay.
So yeah.
Yeah, unfortunately, I didn't talk to the person who basically does the field board, so that's why I didn't have data points on that.
Okay.
So, yeah, that's another thing.
It's a really interesting project.
I really like the cross sections you showed there on your, I guess, second to last slide it was. And I know you said that you just got them on your last day there, but I was wondering if you had sort of a simple geologic model, like how did that shape get there?
So,
Or if
let's go back
it's-
here. So this is an outcrop.
Okay.
So, I mean, either it's,
You think that's
I
what
mean,
you're going to do?
yeah, or a hemisphere or like a semi-cylinder. Because as a physicist, I mean, typically they assume that the world either is a sphere or a cylinder. I mean, physicists tend to do these things to simulate. So,
Any other questions? Good. Thank you.
thank you.